Okay, so I apologize for the late cancellation of class on Friday. I had something come up that I had to take care of Friday and this weekend, but we should be good to go. I posted up a video of what we would have kind of went over, so that's up on YouTube. I extended the due date for the fourth Connect and Excel assignment to be at the end of the day today. If for some reason you had submitted your Connect assignment already and there were specific problems you hadn't worked on, if you want to just do a second submission, you only have to do the problems that you didn't complete, and then send me an email that you have the two submissions, and I'll go back manually after today and kind of combine the points to update it so it shows kind of your total points across both of those submissions. Also, if you would submit the Excel assignment and want to kind of resubmit, I'll grade kind of the newest submission. So feel free to work on that throughout the end of the day. Then we have that fifth Excel and Connect, which are a little bit shorter and probably easier, and that's due at the end of the day on Friday this week. Okay. Any other questions for me that should, I think, cover kind of that stuff? We'll be doing exam review this week, Monday, Wednesday, and Friday. If you have time to start looking through those practice exams that are up on Canvas under the final exam practice materials folder, I'll go over specific problems that people have. Otherwise, like I'm guessing today, based on other sections, I'll probably just kind of start working through and work through that first practice exam. The final will be about, I don't know the exact breakdown percentage-wise yet. I'm still kind of fine-tuning it, but I'm going to say somewhere around like 12 to 15 multiple choice questions, and then a couple, like 2 to 3 short answer, depending on kind of how many, how you would count that. There's going to be multiple parts to each question. So it'll be about a 60-40 breakdown, 60% multiple choice, 40%-ish about short answer. So a little bit different than the previous two exams, but I'll have kind of a 2-hour time block. Once you start it, you'll have 2 hours, so you have a little bit more time than usual. Any questions from me before we kind of get jumping in here to this exam review? Okay. Does everything sound okay too, by the way? Yes?
Yes, it does.
Awesome, thank you. So let's go here. And let's actually start with, get all this stuff out of the way from my previous section. So let's go to Files, Final Exam Practice Materials. We've got, get rid of these here. So Practice Exam B, we'll actually start working on this one today. Okay. Open this up. And then the other thing that we'll have is this formula sheet. So I'll update the formula sheet on Canvas. I had left off a couple things that I wanted to add on there. I have the original, these, which would get us through kind of most of the practice exams, but I updated just to kind of group them together a little bit better. So I'll get that updated after class today. So it'll look a little different. So I'll be working with one that you're going to have available to you. So practice exam B, kind of the first question here, which I wouldn't exactly have it written like this because of the way that we've kind of worked the material, but it's an example that gets some of the stuff that we've talked about. It would relate to. So in which of the following situations we use the standard normal versus the student t distribution, right? Whether or not we're doing confidence for confidence intervals. So or hypothesis testing. So the only examples that we're going to use the standard normal distribution for, if we looked at this formula sheet, here's our confidence intervals, here's our test statistics for 2 populations, which is all the one population stuff is back prior to this exam, so it's not a comprehensive exam, so got to start there. Here's our matched pair stuff. So notice, when we're looking at a matched pair example, or we're looking for the difference in sample means where we only have sample variances, those are the scenarios where we use that student t. If we're looking at the difference in proportions or the difference in means when we know population variances, those are scenarios where we can use that standard normal distribution. So here, when can I use the student t? confidence intervals where we have two population means and the variances are unknown. Right? Well, actually, sorry, let me say this again. This is question section. When do we use the standard normal instead of the student t? Well, here we've got unknown population variances, so that's actually going to be a student t distribution, so that's not it. One population example is where we have an unknown population. Once again, when we don't know the population variance, it's a student t, so that's that. We're looking for when we use a standard normal. Confidence intervals for matched pairs. Well, matched pairs isn't it, right? We just said matched pairs, we're only going to have a sample variance, so student t. Confidence intervals and hypothesis tests when we have two population proportions. Anytime we have population proportions, we know we're using that z-table or those standard normal distribution. Okay? And you know, the formula sheet kind of reminds us of that. But really the only times where we use that standard normal distribution is if we have proportion examples or we're looking for the difference in means where we know population variances. Okay? So here we've got the first example. We've got kind of BMI for Indiana and the BMI for Ohio, right? So we've got two sample means, 28 and 29. We've got 40 people from Indiana, so our first sample size, and we have a sample variance from that group of 9. We then have a sample variance for group 2 of 16, and we have a sample size for group 2 of 50. Okay? So if I take this information, right, and I want to build a 95% confidence interval for the difference between Indiana and Ohio's BMI. Assume that our degrees of freedom is equal to 50. Okay. So we're going to go to our formula sheet. Here's our confidence interval equations. We're looking for the difference in sample means, but we only have sample variances. So we're going to be looking at, here we go, this guy right here. Okay. So all we do, once we've identified the correct formula, we just plug in 28, 29, 9, 16, 40, 50. The only thing left we need is this t value. So it's the t value that gives us alpha over 2 on either side of our distribution and at a degrees of freedom, which is delta. So this delta was, you know, I can go back in the slide, it was that crazy equation I said I'm not going to make you use. I'm always going to give you that assumed true degrees of freedom, or I'm always going to give you delta. So our delta here, our assumed true degrees of freedom was 50. I believe we wanted the 95% confidence interval. So my alpha, the area outside the interval in decimal form, so 95%, 5% outside of it, decimal form, 0.05, divided by 2, so 0.025. So I go to my table, I want 0.025 in the tail at the degrees of freedom of 50. So I go over 0.025, degrees of freedom 50, 2.09, okay? So 2.009 is the value that I'll plug into that t value. And at that point, it's just a matter of making sure I can compute, kind of get this entered into my calculator correctly, or Excel if I want to use that. Okay? So really the key here is identifying the correct confidence interval equation. We have 3 of them here. I'm looking at the difference in means with only sample variances. And it even reminds me, use that student t distribution, okay? So I'll kind of work through these alongside. So let's say, so I'll plug everything in. So 28 minus 29, what was it? We say 2.009 was that value we needed to use. Square root of 9 over 40 plus 16 over 50. So 0.48, right, is going to be our upper bound. Our lower bound is going to be negative 2.48. Okay. Now, if I look at these, can I rule any of these out? Well, if I think about what I'm doing with a confidence interval, I took, right, that sample difference I found between group 1 and group 2. We had this t value of what, 2.009 times filling everything else in. So we're centering our confidence interval around -1 and then finding our upper and lower bound. So the sample difference we found should be smack dab in the middle of our confidence interval. So if we look at the possible answers, -1 actually is right in the middle of these. -1 is not in the middle of these, right? -1 is only about 0.5 away from the lower bound, but 2.5 away from the upper bound. So we could rule this out. -1 looks like it's 0.74 away from this, but 1.26 away from that one. So it's not even in the middle of this interval. -1, we think about, is actually equally as far from both of these. So A or D could be the correct answer. Right? And we already worked it out and we found it was A. But that's how you kind of rule some of them out. That sample difference you find, that's what you're building your confidence interval around, has to be smack dab in the middle. I've got my marker cap. So then we'll move to 3, which is determine what the test statistic would be for the following hypothesis test. Right? Okay, so we've got this test. It doesn't really matter when we're computing test statistics. We're always going to be using these equations, right? It doesn't matter if it's a left or right or a two-tailed test in terms of just getting the test statistic. So which test statistic should we use? Well, we're not dealing with proportions. We are dealing with differences in means, but we only have sample variances. So we need to use this guy right here. We'll plug in those sample variances of 9 and 16, sample means of 28 and 29, sample size of 40 and 50. Once again, once we've identified the correct formula, it's really just a matter of getting these entered into your calculator correctly. Okay, so I think what we should get is -1.35. Now, once you enter that in your calculator. Now, thinking about this here, if we look at that test statistic equation, in each of these test statistic equations, the denominator represents some sort of standard deviation. If it's a standard deviation in the denominator, well, variances and standard deviations are always positive. So if the denominator is always positive, the sign of your test statistic for these two population examples will just be what's the sign of that sample difference you found. Our sample difference was 28 minus 29, so -1. And so there we know our test statistic has to be negative. So we could have actually ruled these positive answers out. And then from there, it was a matter of plugging things in and doing the computation. Okay. Any questions on those before we keep moving here? Okay. So if we use the hypothesis test we found from 18 and this assumed true degrees of freedom of 50, at the 95% confidence level, what is the critical value and the outcome of the test? Okay. So let's say we assume that the test statistic we found, instead of -1.35, is -1.55. Okay. We've got what type of a tailed test? Well, here's our alternative hypothesis. We've got less than 0 here, so a left-tailed test. Okay. So we've got a left-tailed test, and we want to find the critical value and the rejection decision. Okay. So first of all, if we know we have a left-tailed test, we actually can say something about the critical value. So, what am I doing? Sorry, I'm thinking about a different class. So we've got, we're dealing with that student t-distribution. Now we know that it's centered around 0, and we want the critical value that gives us alpha in the tail, which I think the alpha was 0.05. Well, the area to the left and right of the mean, which is 0, is 0.5. So if I want an area to the left of not 0.5, but 0.05, I know my critical value is to the left of 0. Well, what's the left of 0? Negative values. Right. So we want that t-value that represents the critical value such that anything more extreme than my critical value, if I see a test statistic anywhere in this region, I can reject. And the area to the left of that critical value is 0.05. So we've got this assumed true degrees of freedom of 50, right? If I go to my t-table, degrees of freedom of 50, I want 0.05 in the tail, so 1.676, right? Now that's not my critical value because the student t-distribution always or the table, always is looking at the upper right tail. Okay. If I remember that for a left-tailed test, I have a negative critical value. Well, the distribution is symmetric. So if 1.676 gives me 0.025 in the upper right tail, right, then negative 1.676 would give me 0.05. I might have said that wrong before you too. Did I look that up right? It was 0.05, and I think I said 0.025. Let me make sure I looked at the right column there. 0.05 was the, oh yeah, third column. Yeah, so I got that right. So 1.676. But because it's a left-tailed test, it's going to be negative. Right? From there, I was told to assume that the test statistic that I found was negative 1.55. So that would actually be right about here, which is not in my rejection region. So here's my critical value of negative 1.676. And given that assumed true test statistic, I failed to reject the null there, right? Because my test statistic wasn't in my rejection region. So if we go back, right, oh, here we go, negative 1.676, and we would fail to reject. Right? Now, right away on this one, if I remember that for a left-tailed test, my critical values have to be negative. If I looked at the critical values for each one of these, I actually could have ruled all of them out, right? So remembering that for a left-tailed test, critical values are negative, a right-tailed test, critical values are positive, and for a two-tailed test, we'll have a pair of critical values. Just knowing that information, I didn't even have to look it up. I could have got the correct answer here. Okay? Now, it's good to know how to look it up, because if I turn this into a short answer question instead, well, that doesn't really help me, right? So I have to find the exact value. Okay. All right. Let's see here what we got. Okay. So let's assume, we'll start with 5. Let's say we take a recent survey of 250 households from the US and Canada, and we find that gun ownership is at, what, 32% in the US and 26% in Canada. So we want to find the 90% confidence interval for the true difference in gun ownership. And I said men and women here. I forgot to change this. I think I have another example on the other practice exam. So we got US and, oops, Canada here. So kind of identify, question here. I just have 2 questions. Oh yeah. Okay. So it's US compared to Canada. Also, I think there's a small typo here, so we'll change this. So I'm going to identify for you what group 1 and group 2 is, right? So even though I kind of said the difference between US compared to Canada, I've even identified what you should use US as group 1, and let's use Canada as kind of group 2. Okay. So I've got my 2 sample sizes and my 2 sample proportions. All right. Let's go to my formula sheet. I'm looking at the difference in proportions. So this needs to be the confidence interval equation I'm using. From there, it's just a matter of plugging everything in. So I've got 0.32 and 0.26, 0.32, 0.32, 0.26, 0.26, 250, 250. The only thing I really need to look up is this z-value. So I want the z-value, because I'm dealing with proportions, I look at that standard normal distribution. The alpha I have here, so it's a 90% confidence interval. So alpha would be 0.1. I have to divide that by 2 because I have an area to the left and right of my confidence interval. So 0.1 divided by 2 is 0.05. So I'll go to my z-tables, because I'm dealing with proportions. The area I want in that tail is 0.05, so I'm going to look that up. So in between 0.05 and 0.0495, so here's as close as I can get. So negative 1.64, in between that and negative 1.65. I'll take the higher in absolute value of the 2, so negative 1.65. Oops, sorry. That's what I plug in as that z-value I need. Now I could have also found this by using my t-tables, remember, because if I want 0.05 on either side of my interval, if I go down to this last row where the degrees of freedom is infinite, that represents the standard normal distribution. So 1.645, I can get a little bit more precise there. Okay. So then I have that 1.645. I plug that in, right, as that z-score that I needed. So 0.32 minus 0.26 minus 1.645 times the square root of. I'm kind of working these out as I said. I could just look at the answer key, but I want to make sure that, you know, I'm working them out here in real time with you. Did I hit 250 plus? Oh. So negative 0.006. So let's go. So if I round it, I believe I should get negative 0.007 as my lower bound and 0.127 as my upper bound. Okay. Now, if I just think about what I'm centering my confidence interval around, so look here, I took 0.32 minus 0.26. So I was centering, right, this difference is 0.06. I'm centering my confidence interval around 0.06. So 0.06 should be smack dab in the middle of my confidence interval. If I look here, it looks like it's in between, you know, in the middle of these. 0.06 isn't even in either one of these confidence intervals, okay? So that's one, you know, quick first check you can always do. Make sure that that sample difference you found is smack dab in the middle of your confidence interval. Okay? From there, if we wanted to find the test statistic, and now we're kind of dealing with this right-tailed test, let's say, what's the test statistic for whether or not gun ownership is higher in the US, right? So the alternative hypothesis has a greater than sign, so we're dealing with a right-tailed test. For the test statistic, that doesn't really matter, right? We look at the formula sheet, we're looking for the difference in sample proportions. Now, this was kind of the tricky one where we first had to compute this p-bar. So I have my sample sizes of 250, plug those in. I then have kind of the sample proportion of 0.32 and 0.26. So once I plug those in to get my p-bar, I should get 0.29. Okay. So 0.29 is my p-bar. I then plug that in. Well, and then I just plug in my sample sizes and plug in those two sample proportions that I had. So 0.32 minus 0.26 divided by the square root of 0.29 times 1 minus that 0.129, which is that p-bar that we found by plugging our values in there. And from there, we can kind of just plug everything in. We should get approximately 1.47. Now, I could have ruled one of these answers out right away because if I looked at that equation that I had, it had P1 bar minus P2 bar divided by the square root of, P hat, P1 hat and P2 hat. And then down here I had, you know, whatever I had. I don't want to say all this all out just to waste time. But that denominator, remember, it represents the standard deviation for the difference in those sample proportions. Well, if this is a standard deviation, then the denominator has to be positive. Whatever sample difference I find tells me the sign of my test statistic. So because I found that sample difference between the two is what, 0.06, 0.32 minus 0.26, I know the test statistic has to be positive. So when I'm looking here, right away I can rule out B. Can't really rule the other answers out, although 36 seems like an extremely large test statistic. If I'm just taking a guess at this one, I'm probably going to go with either C or D. Okay. From there, if I have a right-tailed test, right? So this greater than sign of the alternative hypothesis, same thing I use in problem 7, I have a right-tailed test. So in case you got the test statistic wrong, I give you an assumed true test statistic. So assume it's 1.67. What would the p-value be? And would I reject or fail to reject if the alpha was 0.05? Okay, so we'll use 1.67 as the test statistic. So for a right-tailed test, the p-value represents the probability that I saw the test statistic that I did, or anything larger in absolute value, or anything more extreme that goes against that null hypothesis. So for a right-tailed test, anything to the right of my test statistic. Well, if I go to the standard normal tables, if I look up 1.67, I can get the area to the left, but I want the area to the right, so I would have to then subtract that from 1. Okay? So I go to my table, and I look up that test statistic of, scroll down, 1.67.9525. Okay? So 0.9525 is the area to the left. I wanted the area to the right, so I subtract that from 1. I get what? 0.0147. Okay? So that's my p-value. All right, so we'll go back here. Let's look at the answers that we're given. So 0.045, I would have to make my rejection decision because once I get the correct p-value here, right, I can identify the correct answer. Now, if I instead had, like, I don't know, given you something like this, how do I know if I reject or fail to reject? Well, we only reject if my p-value is less than alpha. My p-value is 0.0475, and that in fact was less than 0.05, so I am able to reject the null here. Okay. Any questions on that one? Okay, so here's the correct answer. Now, what if instead I asked you for the critical value? If our alpha was 0.05, the critical value for a right-tailed test, right? We're dealing with that standard normal distribution, or z-values. I want the critical value that gives me 0.05 in that upper right tail. Okay. Well, you can do this one of two ways. I could say, okay, I'm going to use that standard normal table and look up on the z-table. The area I want in the right tail was 0.05. So the area that I want to the left would be 0.95, right? 1 minus that. So I can look up 0.95. It's in between these two values. So 1.64 and 1.65. So I could use kind of the higher of the two there, 1.65. Or I could have said, well, look, if I want 0.05 in the upper right tail, if I use this student t table and go all the way down to the very last row, this gives me those standard normal distribution values, and it's a little bit more precise. So instead of being between 1.64 and 1.65, I can say that's exactly 1.645, right? So my critical value here would be 1.645. Now, similar to the last one we said, remember, both the student t and the standard normal distribution are both centered at 0. The area to the right of 0 will be 0.5. The area I want to the right is 0.05. So I know my critical value has to be to the right of 0 or has to be positive. Right? So right away, if I, oh, sorry, this wasn't, this is a question I was kind of creating. It wasn't on the exam. So right away, I know my critical values for a right-tailed test have to be positive, greater than 0. And I also could think about that test statistic that I had, which I'm already forgetting what it was. So we had to assume it was what? 1.67. If I plot that, right, it's just barely inside here. So it's in my rejection region, so I would, be able to reject, right? Which is the same thing that we said before. And in fact, before we were saying we could barely reject too, because 0.0475 is barely less than 0.05. Right? So no matter which kind of approach we use there, we'd come up with the same rejection decision. Any questions on that? Before we keep moving here. Okay, so we'll go through just these next two questions and we'll save the linear regression stuff for next class. So in 2009, there was a federal minimum wage law passed. We looked at 81 different counties and we found the unemployment rate for these counties, difference between these two time periods, was a change of negative 1.2%. And the variance on these differences was 3.2%. So the researchers then, so actually also, I'll get this updated, man. I didn't notice there's all these typos. So it's negative 1.2%. Here I just kind of trying to give you the actual, statistic, sample statistic. The sample difference is also, would be negative 1.2. So the researchers decided they wanted to test for whether or not there was a difference in the unemployment rate and whether or not that difference was negative. Right? So whether or not after this change, the new unemployment rate was lower, right? It decreased. If the increase was negative, we're seeing a decrease. Kind of probably wouldn't word on the exam like this. I grabbed this example from something because I liked the idea of it, but it's I don't like that phrasing. So let's assume, right, that this is our setup. What would our test statistic be? Well, if we look at our formula sheet, we've got our matched pairs. The talk's not happy. So we've got our matched pairs example. Here's our test statistic for matched pairs. We've got, technically there's an assumed true difference here, but it's always 0. So it doesn't do anything. So we take our sample difference, divide it by the standard or the square root of the variance for that difference divided by the sample size. So this denominator represents the standard deviation for these sample differences, right? That will always be positive. So whatever sample difference we find tells us the sign of that test statistic, okay? Hold on, give me 1 second. I'm going to put a dog because apparently he's upset. Okay. All right, brief interlude. Hopefully they're not. I'll stop barking out there in a second. So, where were we? So we've got this test statistic, and we know that the sample difference is negative 3.2. That would tell us the sign. So automatically, we know that we should end up with a negative value here, right? Because the denominator of that test statistic is a standard deviation, so that's always going to be positive, okay? But from there, it's just a matter of plugging everything in, right? So we had negative, I think I said 3.2. I believe it was actually negative 1.2. Yeah, negative 1.2. The variance was 3.2, right? So divided by the square root of 3.2 divided by the sample size of 81, we get a test statistic here of about negative 6. Right? So from there, what would the critical value for this test be and what would the rejection decision be, assuming that instead of negative 6, we found this test statistic of negative 1.5. All right, well, the formula sheet kind of reminds us that when we're dealing with these matched pairs examples, we're using the student t-distribution. Okay? So what I want, right, is the critical value. And I believe we had I think I already mentioned this, but it's just to reiterate, to show you, we have a less than sign in the alternative hypothesis. So we have a left-tailed test. So automatically, we know that our critical value should be, for a left-tailed test, we said earlier, negative. Okay. Now, what area do we want in the tail? Well, here we've got what? 90, an alpha of 0.05, right? So alpha is 0.05. So we want the critical value is this 0.05 in that lower left tail. But here, when we have a matched pairs example, I'm not going to give you the assumed true degrees of freedom because it's a little bit easier to calculate, which is simply n minus 1. So here, I think our sample size was 81. Or we get degrees of freedom of 80. Okay. So we go to our student t table. We look at the degrees of freedom of 80. The area in the tail we wanted was 0.05. So where do those two meet? 1.664, right? So our critical value, right, here is going to be 1.664, but for a left-tailed test, remember that student t-table always looks at the right-hand side, so it's that value, but negative. If we then had an assumed true test statistic, and I think it was negative 1.5, well, where does that fall? Right outside of our rejection region, so we would fail to reject. Let's say instead I had an assumed true test statistic of 2.5, well, that would be somewhere over here, sorry, negative 2.5, that'd be somewhere over here, and I would reject, because that would be in the rejection region. But I think the actual problem gave us that, negative 1.5. So ultimately, the answer, too many tabs, is going to be negative 1.664 is our critical value, and we failed to reject if the test statistic was in fact negative 1.5 as we were told. Okay. And remember, the reason I give these assumed true test statistics and things like that is because I don't want to have you have cascading errors. Like if I get 8 wrong, then I don't want you to automatically get 9 wrong because you're working with like a faulty test statistic. Okay. One more thing I want to show you in this problem is let's instead assume we had a question about what's the critical value. Well, these matched pairs, we're using the student t-distribution. Right? So when I'm thinking about the p-value instead of the critical value, what I'm actually thinking about is with that test statistic of negative 1.5, the p-value is the probability I saw that test statistic or something more extreme, something further from that assumed true difference. So I want to find the area to the left of negative 1.5. Okay? So I go to my student t-table, and the problem is that at degrees of freedom of 80, well, first of all, even if I remember this is symmetric, so I think about all these as negative values, where is negative 1.55 here? I can't find it. But it would be in between negative 1.29 and negative 1.66. So the areas to the left of negative 1.29 and negative 1.66 would be 0.1 and 0.05. So because my test statistic was in between those two values, I know that the area to the left of my test statistic has to be in between 0.1 and 0.05. So I can't give you an exact p-value, but I can tell you that it's somewhere in between negative 0.05 and negative 1.0. But that's all I can do. And at that point, well, if the p-value is somewhere in this range, can my p-value be less than that alpha of 0.05? Well, no, it can't. And so I would fail to reject. Any questions on any of that before, I think we'll probably kind of wrap it up here for today. A little bit short, but we got through the questions I wanted to go through. We'll save the linear regression stuff for next class. And what I'll likely do is I might bring in some additional questions on Wednesday because I recorded for the other section practice exam A, which you guys have the same practice exam. So I'll probably just post up both videos today. So you'll have what we just worked through, but you'll also have me working through practice exam A. And then that will give us a little bit more time if people want to meet live to actually go through, even if it's the same practice exams, you're just like, I know you went over that, but I don't quite understand what you meant here. That gives us a little more time to do that, okay? So that's kind of the game plan. Any other questions for me before we kind of just end this video? And if you have some questions about homework or anything, feel free to kind of hang around after. Okay. All right. We'll end the video here, and I will see you guys on Wednesday.